Have you ever just stopped and wondered what makes everything, well, tick? You know, from the stars burning billions of light years away, all the way down to the smartphone you're probably holding in your hand? Turns out there is a fundamental set of rules, kind of like an operating system for reality itself. And today, we are going to take a journey through that very operating system: physics. So that leads us to the big one, doesn't it? This is the question that's been driving human curiosity for, well, forever. It's not just about seeing what things do, but understanding the deep, universal laws that dictate why they do it, from how a planet orbits a star to how a single particle behaves. And here's our answer. At its very core, physics is the study of two fundamental things: matter, which is basically all the stuff in the universe, and energy, which is the ability to make all that stuff do something. So really, physics is this incredible quest to understand the relationship between them and to, write down the rules for how they interact. Okay, so to really get our heads around this, we're going to go on a journey through scale. And we're starting big. I mean, unimaginably, mind-bogglingly big. Welcome to the macrocosm, the realm of galaxies, black holes, and the huge, sweeping architecture of space-time itself. Now, at this cosmic scale, two major branches of modern physics are in charge. First, you've got astrophysics, which tells the life story of stars, how they're born, how they live, and how they die in these spectacular explosions. And then there's relativity, Einstein's masterpiece. It completely flipped our understanding of gravity. It showed us that gravity isn't some mysterious force pulling things together. No, it's actually a curve, a warp in the fabric of spacetime. This means planets aren't being pulled by the sun, they're just rolling along the straightest path they can find through a universe that's been bent by mass. Just think about that for a second. It's an absolutely wild idea. All right, let's zoom in from that cosmic dance and bring it all the way back home, right here to Earth. This is what we call the human scale. It's the world we see and feel and interact with every single day. And believe it or not, the very same fundamental rules are at play here, just in ways that are a little more familiar to us. The physics of our everyday world, it really starts with mechanics. Let's say you're trying to push a car. The force you apply, that's the actual push that gets it going. The car's resistance to moving in the first place, that kind of stubbornness, that's its inertia. And that dragging feeling from the road slowing you down, that's friction. Those three simple concepts, they explain pretty much every single motion we see around us. Next up, we have thermodynamics, and this is all about heat and energy. Yeah, it explains how your car's engine turns heat into motion, but it also explains something way more profound. It's why things tend to happen in one direction. It's the reason your coffee always gets cold and never ever spontaneously heats itself back up. In a way, thermodynamics actually defines the arrow of time. You know, for the longest time, we thought electricity and magnetism were two totally separate things. But physics came along and revealed that they're deeply connected. They're just two sides of the same coin, and we call that coin electromagnetism. Now, this single, unified force doesn't just power our world. It's actually responsible for the most basic thing we experience: light itself. That's right, light is an electromagnetic wave. And of course, physics also explains how we perceive the world. You have acoustics, which describes the vibrations that our brains interpret as sound. And then you have optics, which explains the behavior of light that allows our eyes to see. So when you put them together, they're basically the physics of our senses. Okay, so we've explored the vastness of the cosmos, we've covered our everyday world. Now, for our final jump in scale, we're going down, way, way down. We are diving into the microcosm, the hidden, bizarre, and absolutely fantastic world inside the atom. And just a warning, this is where everything we think of as normal gets completely thrown out the window. So to make sense of this strange place, we need two more branches of physics. There's nuclear physics, which explores the atom's tiny, super dense core and the unbelievable energy that's locked up inside. And then there's quantum mechanics, the fundamental and, let's be honest, seriously bizarre rulebook for reality. You have to forget about certainty. Down here, it's a world of probabilities, where a single particle can literally be in multiple places at once until the moment we look at it. It is the strange, shimmering foundation that sits underneath everything we know. So how on earth do we connect the physics of an entire galaxy with the physics of a single tiny quark? What's the common thread that ties all this together? Well, the universal language is mathematics. From Einstein's E equals mc squared to Schrödinger's wave equation, math is the powerful, elegant tool we use to describe and predict and unify all of these different scales. It's basically the source code of the universe.
And here it is, our entire journey, all in one view. We started way out there in the cosmic dance of relativity and astrophysics. Then we zoomed into our familiar world of mechanics and thermodynamics on the human scale. And finally, we dove deep into the strange quantum world inside the atom. You see, it's not a bunch of separate subjects. It's one continuous, connected spectrum of understanding reality.
So, the ultimate takeaway here is that physics isn't some dusty old book of facts that's already finished. Not at all. It's a living, breathing quest. It's our map of reality. And as this final thought reminds us, that map is far from complete. The greatest adventures, the most profound discoveries about the operating system of our universe, they're still out there, waiting for us. The only question is, what do you think we'll find next?